You know, we usually think of chemical reactions as a one-way street, but some of them are more like a constant game of push and pull, a delicate balancing act that's happening all around us in places you would never expect. And today, we're going to break down exactly how that works.
It really all starts with a pretty simple question. We've all cracked open a bottle of soda and heard that awesome shh sound as the fizz escapes, right? But have you ever stopped to think about how it stays so perfectly carbonated when the cap is screwed on tight? Well, it's not magic. It's a beautiful chemical balancing act.
So, most of the time, when we picture a chemical reaction, we think of it as a one-way trip. Stuff A and stuff B combine to make stuff C, and that's the end of the story. But it turns out that's not always the case. Some reactions are way more like a busy two-way street, with traffic flowing in both directions at the very same time. Just think about burning a piece of wood. It turns into ash and smoke, and there's no way you're turning that ash back into a log. That's what we call an irreversible reaction, and you'll see it written with a single arrow. It's done. But the real star of our show today is the reversible reaction, and it's got this special double arrow. This little symbol is your big clue. It's telling you that, yeah, the reaction can go forward, but it can also go backward.
So what does that really mean? Well, a reversible reaction is basically one where the stuff you make, we call those the products, can actually turn around and react with each other to remake the exact things you started with, the reactants. It's pretty wild.
Let's look at a classic example here. You've got hydrogen gas and iodine gas. They can combine to form a new compound, hydrogen iodide. But, and here's the cool part, at the very same time in the very same container, that hydrogen iodide is splitting back apart into hydrogen and iodine. Both of these things are happening at once.
Okay, so if the reaction is constantly going forwards and then turning around and going backwards, how does anything ever settle down? It sounds kind of chaotic, right? Well, the secret isn't in the amount of stuff, it's in the speed of those reactions.
So, inside our little reaction container, we've got two competing processes. You have the forward reaction, where our reactants are linking up to make the products, and then you have the reverse reaction, where those products are breaking down and turning back into reactants. It's this constant cycle.
Picture this. You just mix the hydrogen and the iodine together. At that very first moment, you have a ton of reactants and basically zero products. So the forward reaction kicks off super fast, right? But the reverse reaction, well, it can't even start yet because there's nothing to reverse. But as that forward reaction starts doing its thing, it begins to create the hydrogen iodide. And now, finally, the reverse reaction has some fuel. It can get started. And the more product you make, the faster that reverse reaction gets. And this brings us to the absolute heart of this whole idea. Eventually, you reach a point where the forward reaction has slowed down a little, and the reverse reaction has sped up enough that their speeds are perfectly matched. They become equal.
This perfect balancing point has a name. It's called chemical equilibrium. And here is the single most important thing to remember. Equilibrium is not about having equal amounts of reactants and products. It's all about the rates, the speed of the forward reaction and the speed of the reverse reaction being exactly the same. Now, you might be thinking, okay, if things are being made and unmade at the same rate, doesn't everything just stop? Like the reaction just freezes in place? And the answer is a big emphatic no, and that's why we call it a dynamic equilibrium. The best way to understand this is the escalator analogy. So, imagine people getting on an escalator. That's our forward reaction. At the same time, people are getting off the escalator at the top. That's our reverse reaction. Now, if two people get on every minute and two people get off every minute, what happens? The total number of people on the escalator stays exactly the same.
But here's the key. Even though the number of people isn't changing, the escalator itself is in constant motion. The individual people are always moving. It's exactly the same with molecules. The reaction never, ever actually stops.
So that gives us our full official definition. Dynamic equilibrium is a state of balance where the reactions are still going, forward and back, but because their rates are equal, the overall amounts of everything in the mixture just look like they're staying constant. It's like this hidden microscopic dance that's always happening.
So, why do we care about any of this? Is it just some weird concept for a chemistry textbook? Absolutely not. This balancing act is happening all around us, and it is responsible for some incredibly important things in our world.
So let's go all the way back to our soda bottle. Inside that sealed container, The carbon dioxide gas that's in that little empty space at the top is constantly dissolving into the liquid. At the exact same instant, dissolved CO2 is bubbling back out of the liquid into a gas. The rates are perfectly equal, creating a dynamic equilibrium that keeps that soda perfectly fizzy, right up until you break that seal.
Okay, fizzy drinks are one thing, but the stakes get much, much higher than that. Understanding equilibrium is literally a matter of life and death on a global scale.
This is called the Haber process. For a long, long time, scientists struggled to figure out how to pull nitrogen gas, which makes up most of the air we breathe, into a form that plants could actually use to grow. The answer was this reversible reaction, which creates ammonia. By learning how to control and manipulate this one specific equilibrium, chemists unlocked the key ingredient for all modern artificial fertilizers.
And the impact of that is just staggering. It's estimated that nearly half, 45%, of the entire world's population is fed by crops that rely on fertilizer made from this one, single, carefully controlled, reversible reaction. That is the power of understanding equilibrium.
Okay, so let's pull it all together real quick. The big takeaways are, some reactions are a two-way street, marked by that double arrow. They find a perfect balance, called equilibrium, not when the amounts are equal, but when the speeds or rates of the forward and reverse reactions match up. And finally, it's dynamic because that molecular dance never actually stops, even when things on the surface look perfectly still.
Which, of course, leaves us with one final, really fascinating question. We've established that equilibrium is this perfect dynamic balance. So, what happens if you mess with it? What if you try to push it, maybe by adding more reactants or cranking up the temperature? How does the system fight back to find that balance again? Well, that is a story for another explainer. Thanks for tuning in.